All right, so we're on the area of circles and sectors worksheet, and we're doing number 11. Number 11, you are looking for what we defined as a segment yesterday. This is called a segment of a circle. And we learned yesterday that it's a little bit of a lengthy process, not yesterday, but Wednesday, it's a little bit of a lengthy process to find the area of a segment of a circle. Because you have to do the area of the sector minus the area of the triangle, and that will give you the area of the segment. So let's start by finding the area of the sector. The area of the sector is going to be this part right here, the whole piece of pie, like that. So we're going to find the area of that by doing A sec over A equals M over 360, because I teach it the proportion way, but if you like the multiplication way, that's fine. So we do 144 times 60 divided by 360, and we get 24. So the area of the sector is 24 pi. Make sure, good job. Make sure you're not forgetting that pi. If you forget the pi, the answer is going to be completely wrong. You're going to do all that work and get the problem wrong. All right, the next part is the area of the triangle. So the part we don't want is the area of this triangle right here. So what I'm going to do is I'm going to redraw that triangle. I'm going to draw it right here. I know that this is a radius and this is a radius. So I know that the triangle is at the very least, it's isosceles, at the very least. But wait a minute, the central angle is 60. So that means that this angle right here is 60. Now, if I've got an isosceles triangle with a vertex angle of 60, then automatically that's an equilateral triangle, because the angles left have to be congruent, and the only way to divide 120 by 2 is to get 60. So that is actually an equilateral triangle. And we talked about a shortcut to find the area of an equilateral triangle. It's sine squared root 3 over 4. But if you have not committed that to memory, then you could just find the area of that triangle. Base times height divided by 2. So side squared, so that'd be 144 divided by 4. And we get 36 root 3. Is that okay with everyone? Those are not like terms. Those are non-combinable. Combinable. So if some of you are having trouble with the way that I got 36 root 3, this is 6, and the height of the triangle is 6 root 3. So the other way to get it would be base times height divided by 2. That's the long way to get it if you didn't memorize that formula. What is a tangent line? Okay, let's remember. A secant crosses a circle exactly 2 times. A tangent intersects a circle. A lot of people are typing. What are you going to say? What are you going to say? One time. Exactly 1 time. Yep. So you kind of think of it as something that just barely skims the circle. So in my green picture, I've got examples of tangent lines. There's always going to exist a point of tangency, a point of tangency, point of tangency, point of tangency, and then an example of what would not be tangent. This one's touching the circle twice, and touching 0 times. So none of those would be tangent lines. A reminder, we already went over this in our notes, so you don't need to add this to your notes because you already have it on your vocab notes. But a reminder is that when you draw a tangent line, at the point of tangency is perpendicular to the radius. So this is a radius of our circle. This is our tangent line. And when they intersect, every single time, you get a right angle. Every time. Thanks? Okay. So, let's see if we can come up with our first theorem of the day. So, I'm going to take a point outside the circle. I'm just going to grab a point. Let's call it A. From that point A, I'm going to draw both of the tangents that come from that point. That was one of your homework problems a couple days ago. It was asking how many tangents can you draw through a point that's not in the circle. And the answer was 2. You can draw 2 tangent lines from a point not in the circle. What I'm asking is, what do you think is true about the length of that segment and the length of that segment? What do you think is true about the length of this one and the length of this one? Yeah! And we're not supposed to assume, right? We're not supposed to assume. But when there's a theorem out there that some wonderful mathematician has already proved, then we are allowed to believe it. It becomes part of our textbook. So this is a true theorem. We're not assuming it has been proved. 2 tangent segments from an exterior point are congruent. Notice, those are tangent segments because a tangent's a line, so we're just talking about the segment, like the distance from A to B and the distance from C to B. This is a theorem, so yes, it's always true. So if both of the segments come from the same point, they have to originate at the same point. It doesn't matter how far away you put the point. So let's throw a point right here. Point D. If I, let me get out my math tools, because if I try to just draw this by hand, I'm going to mess it up. If I draw a line, wherever it's tangent to my circle, that is the same length to wherever that one hits the circle. The theorem is that those, because of where they're coming from, how they hit the circle, are going to be the same length. You could do a proof of this. We're not going to prove it, but you could do a proof, and you could prove those triangles congruent. And once you prove the triangles congruent by CP/CTC, then you could prove that those 2 segments are congruent, but we're not going to prove it in class. All right. Next theorem. Read that sentence and figure out what you think goes in the blank. Read the sentence and figure out what you think goes in the blank. Who's going to type it first? Bisects! Very good. So, if I've got my 2 little congruent tangent lines, let's put a tick mark on them. If I've got my congruent tangent segments, and I draw a segment from that point, the exterior point, to the center of the circle, it automatically bisects that angle. And once again, it comes from the fact that triangle 1 is congruent to triangle 2, and so if those are congruent, then their pieces are congruent. And that is where it comes from, by the way. Here's the actual theorem, the actual slide that says the theorem. Next thing that we're going to talk about is called a common tangent. So a line that's tangent to 2 circles at one time is called a common tangent. Now these circles do need to be coplanar just in case you're working in 3D. So we've got 2 types of common tangents. We've got internal and we've got external. They're internal tangents if they break the plane between the 2 circles. So if they come within that plane, they're an internal tangent. And then obviously if they're not breaking this plane right here, then they are an external tangent. So go ahead, don't draw the planes that I drew, but go ahead and sketch yourself a quick picture of that so that you know the difference between the internal and the external ones. If you draw multiple internal tangents, they're going to form you a little X right there. All right. Did you know that circles can also be tangent to each other? Whoa! So if they are tangent to each other, then they're called tangent circles. There's also 2 types of tangent circles, internally tangent and externally tangent. The internally tangent kind of looks like a cartoon, like eyeball or something. But anyways, they're internally tangent if one of the circles is inside the other, and they're externally tangent if, this one It's on the exterior of that circle. So this one's in the circle, this one's exterior. Yes? This one kind of looks like a guy with a really big nose. Like his profile, you see it? Oh. Kind of cute. Okay, moving on. So, let's see if we can name how many common external tangents / internal tangents can be drawn. So we're all going to look only at A. Just look at A. Tell me how many external tangents you can draw and tell me how many internal tangents you can draw. So I've already kind of given you that picture in the notes. We can do this one together. How many external tangents can you draw? 2. We'll do internal and external. How many internal tangents can you draw? I can't think of any more I could draw. So with that basic picture, we've got 2 and 2. Unless y'all can think of another one, let me know. All right, let's look at B. (32 internal? Let's look at B. How many external tangents can I draw? Still 2. How many internal tangents can I draw? Very good, Tahani. 1. All right, let's look at C. Looks like I'm writing Internet Explorer over and over. How many external tangents for C? So remember external, well, let's do internal. Internal is when the tangent breaks the plane between the two circles. But these circles don't really have a plane between the two circles. There's really no space between them. So when I draw this tangent, we know there's only one tangent that touches both. There's only one. So is that one I drew, is that an internal or an external tangent? It's not between the two circles, so we're going to call it an external, 1 and 0. All right, letter D, internal, external. 2 external, we're okay with that. How many internal? I can't draw a line that's tangent to both of them that's between both of them. None. Very good. And E, internal, external. There does not exist a line in this universe that you can draw and is tangent to both of those circles at once. Doesn't exist. 0, 0. This is fun, isn't it? Isn't this more fun than find the volume of the sphere? All right, let's see if we can solve this. I'll give you a minute to think about it. So something that you need to commit to your memory is that when a radius meets a tangent line, you get a right angle. So I want you to picture Miss Tanton doing that really annoying thing in your head over and over. When a radius meets a tangent line, you get a right angle. Well, this is the radius and this is the tangent line. Anyways, when a radius meets a tangent line, you get a right angle. I want you to say it over and over and over again in your head until you're so annoyed that you commit it to memory. So when a radius meets a tangent line, you get a right angle. Let me tell you what students do. Here's what you're not going to do. Are you ready? Here's where some students put the right angle. Boom. They put it right there. It happens every year. It's going to happen. One of you is going to do that. Don't be the person that does it. The right angle goes right here. So BA is 12, AC is 5, and CB is 13. We want to find BD. So we're doing 13 minus 5 for a total of 8. What's wrong? Get it right here. Ha ha ha. That's funny. Miss Tangent. Oh man. Okay, let's keep going. Example 2. ABC is a circumscribed triangle. If the perimeter is 100, find AX. So we learned a little nifty theorem that said, hey, if I draw two tangent lines from a point, those tangent lines are the same length. Well then, those tangent lines better be the same length, and those tangent lines better be the same length. Normally I would give you some time to work this problem and I wouldn't say a word, but we are running out of time, so that's why I am explaining these. So, 26, 26, 8, 8, and we need to find AX. So, 26 times 2 plus 8 times 2 minus 100 divided by 2. What are y'all getting? I got it. What'd you get? Subtract from 100 and divide by 2 because AX is congruent to AY. What do you get? Why are the top ones not congruent to the bottom ones? Because this is not... A, B, and C are all different, we're assuming, because we can't assume, they're all different distances away from the circle. Good job, Quan. 16. X is not a midpoint. X, Y, and Z are not midpoints. They're not midpoints. So you have to use the theorem that says the tangent lines coming from the same point are congruent. And 8. How did I get 26? They were given to us. See how it was typed in there? Okay. Oh, yes, I did, Carson. Oh. I asked her to cut a little bit off, and she like whacked my hair off. Next time I'm going to use the word trim. I'm not going to use the word cut. Anyways, y'all don't care. Okay, let's do this next one. AC is a common tangent. AE is 10. BD is 3. And BC is 12. Okay, ready? When a radius meets a tangent line, you get a right angle. When a radius meets a tangent line, you get a right angle. So make sure you put the right angles where they're supposed to go. Do not put it at angle E. Do not put it at angle D. I noticed hair. You're so funny. Okay, so what do you want to do? Good old Pythagorean theorem. 3 squared plus 12 squared. We're going to have some radicals here. Pythagorean theorem, 3 root 17. Yeah. Okay, what else do you want to do? What else do you see? How are we going to get our other missing ones? So do y'all want to use similar triangles and do a proportion? These triangles are similar. They're similar by angle, angle, squiggly. So we can say 3 is to 10 as 12 is to AC. Is that okay? All right. So 10 times 12 divided by 3. AC is 40. 40 minus 12 will give us 28. Are we okay with this so far? We used a proportion to help us find AC because those are both, they're similar. We've got right angles and we've got a shared angle. CD, we already found it. And uh-oh, ED. Yuck, E. Let's use our same proportion. 3 is to 10 as 3 root 17 is to EC. Well, this is nice. 3 root 17, so 10 root 17. So EC is 10 root 17. So ED is, that's my birthday, 7/17. Ah! Wow. So, are we okay with that? That really was not a lot of circle stuff. That was like similarity stuff. That was proportions and radicals. My birthday has a radical. Everybody's birthday has a radical. Okay, last problem. And also most difficult problem. So let's mark what we know. AE is 15, BF is 6, and CD is 20. What are we going to do? What are we going to do? Sorry, I can't sing, but I had to. So what do y'all think? Do you see some radii? This isn't too bad. EC is 15 because it's a radius. DF is 6 because it's a radius. So EF is 41. That wasn't the tough part. What about AB? Yikes. I think that you're going to have to draw another segment in there that's not already drawn. The radius of the big circle is 15. But my hint is, because you have to add something to your picture, you have to draw something. And a lot of people, when they draw something, they're tempted to do like, well, we know, okay, anyways, they're tempted to do something like that. Oh, it's a right angle. But that actually won't get you anywhere. So the segment you really do need to draw is this segment right here. Wait, Brandon, you're cheating because you knew that because you... No, you're not. Never mind. I was going to say you learned this lesson yesterday, but you didn't. And then notice, so this is going to be a rectangle. And then this is a right angle because when a radius meets a tangent line, you get a right angle. So you've got, once you find this segment right here, once you find X, it can help you to find AB. And this is 6 right here, right? Because if it's a rectangle, opposite sides are congruent. So 15 minus 6, and then you can do Pythagorean theorem. Cool. That is awesome insight, Brandon. Okay, we will reveal the answer on Monday. Have a great weekend.